You learned it wrong. The diagram in your science textbook, electrons circling the nucleus like tiny planets, that picture is false. Physicists figured that out over 100 years ago. A real orbiting electron would destroy itself in less time than it takes light to travel 1 inch. So what is an electron actually doing? We're going to find out. We'll meet the physicist whose doctoral thesis was so radical his professors almost failed him. We'll look at the actual shape of electron clouds, and we'll hit the moment science proved that electrons exist in multiple places at once. If you enjoy this, like and subscribe. It genuinely helps. Let's go. You've seen the diagram 1,000 times. A nucleus sitting in the middle, electrons circling around it in clean, neat rings. Maybe your teacher drew it on the board. Maybe it was printed in your textbook with little arrows showing the path. It looks logical. It looks clean. It looks like a tiny solar system. It's wrong. And here's the part that should bother you. Physicists have known it's wrong for over 100 years. They figured it out before your parents were born, before your grandparents were born. Yet the diagram kept getting printed, kept getting drawn on chalkboards all over the world. Why? Because the wrong picture is easier to draw. The real picture is stranger than most people are ready for. And that's exactly why we're starting here. Because once you see what's actually going on inside an atom, you can't unsee it. It changes what you think matter even is. So let's start with the model everyone knows. A dense, positively charged nucleus at the center, electrons orbiting around it, held in place by electrical attraction, the same way gravity holds the moon in orbit around Earth. The idea made sense. It was visual. It was satisfying. Ernest Rutherford proposed the basic structure around 1911 after a famous experiment where his team fired tiny particles at a sheet of gold foil thinner than a human hair. Most particles passed straight through. A few bounced back. That told Rutherford the atom was mostly empty space, with something tiny and dense right in the middle. The nucleus was real, confirmed, but where the electrons went and what they were actually doing out there in all that empty space, that remained an open question. And the answer, when it finally came, turned out to be one of the most disturbing things science has ever discovered. Because here's the problem with electrons neatly orbiting a nucleus. An electron is a charged particle. When a charged particle moves in a curve, it's constantly changing direction. Changing direction counts as acceleration in physics, even if the speed stays the same. And classical physics, the rules that govern science for centuries, says any accelerating charged particle must release energy as electromagnetic radiation. So an orbiting electron should be bleeding energy the whole time it circles the nucleus. Every loop, every fraction of a second. And if it's losing energy, it slows down. And if it slows down, the pull of the nucleus drags it inward. And it spirals tighter and tighter, faster and faster. Scientists calculated exactly how long this process would take. Less than 100 billionth of a second. To picture that, consider this. Light travels about 1 foot per billionth of a second. 100 billionth of a second is roughly the time light needs to cross a single inch. In that tiny sliver of time, every orbiting electron in every atom in the universe should have already collapsed into its nucleus. Every atom, gone. You wouldn't exist. The chair you're sitting on wouldn't exist. The air around you wouldn't exist. So the fact that you're here, listening to this right now, is direct proof that electrons aren't doing what the textbook diagram shows. Matter is stable. Atoms hold together. Something is stopping that collapse. And the answer required tearing apart everything scientists thought they knew about particles, waves, and the nature of reality itself. The story of how they found that answer starts with a contradiction at the heart of light, and a question nobody was brave enough to ask until a French aristocrat sat down to write his doctoral thesis. Picture the most destructive countdown imaginable. Every electron in every atom in the universe, spiraling inward, collapsing, the entire physical world eating itself from the inside out. all matter dissolving in less time than it takes to blink, less time than it takes to breathe, less time than it takes a single heartbeat to begin. That is exactly what classical physics predicted would happen. And the fact that it didn't happen wasn't a minor curiosity. It was a crisis. A full breakdown of the rules scientists had trusted for 200 years, the equations that described electricity, magnetism, and light. The equations James Clerk Maxwell had assembled into one of the greatest achievements in scientific history led directly to this conclusion: stable atoms are impossible. Every physicist in the early 1900s knew this problem. They called it the instability of the classical atom, and for years nobody had a real answer. Some tried to patch it, some tried to modify the equations, some suggested maybe electrons weren't really accelerating, or maybe the rules changed at tiny scales. None of it held up. The problem ran deeper. It wasn't a calculation error, it was a sign that something fundamentally new was needed. The universe at the scale of atoms was playing by rules that nobody had written down yet. And here is what made it personal. This wasn't about abstract equations on a blackboard. The stability of matter is the reason you exist. Your body is made of atoms. Every cell, every molecule, every strand of DNA in your body holds together because electrons stay where they're supposed to stay. If the classical model was right, none of that would be possible. The crisis wasn't just a physics problem. It was a question about why reality is allowed to exist at all. Enter Niels Bohr. Born in Copenhagen in 1885, Bohr was the kind of thinker who couldn't leave a contradiction alone. In 1912, he joined Rutherford's laboratory and immediately started wrestling with the collapse problem. He couldn't make classical physics solve it, so he did something unusual. He stopped trying to explain and started demanding. Bohr simply declared that electrons were only allowed to orbit at certain specific distances from the nucleus. At those special distances, they would not radiate energy, they would not spiral, they would just stay there, locked in place, stable. No classical physics supported this rule. Bohr offered no mechanism, no explanation for why those orbits were special. He just said they were, and moved on. It should not have worked. It was the scientific equivalent of drawing a line on the ground and saying gravity stops here. Except it did work. For hydrogen, the simplest atom with just one electron and one proton, Bohr's model predicted the exact colors of light that hydrogen atoms release when they get excited. Scientists had been measuring those colors for decades without understanding them. Bohr's rule explained every single one with breathtaking mathematical precision. He won the Nobel Prize in Physics in 1922 for this work. But the rule had a dirty secret. The moment anyone tried to apply Bohr's model to an atom with 2 electrons, the math fell apart. The predictions stopped matching reality, and Bohr himself admitted it. His model had no physical foundation. He had stopped the collapse by inventing a restriction without knowing why that restriction existed. The real answer was still missing. And it was hiding in something nobody expected. Something that had nothing to do with electrons at all, and everything to do with the strange double life of light. In 1911, a physicist named Ernest Rutherford set up one of the most elegant experiments in the history of science. His team took a sheet of gold foil. They made it incredibly thin, just a few hundred atoms deep. Then they aimed a beam of tiny positively charged particles at it, particles moving so fast they were essentially atomic bullets. The expectation, based on the science of the time, was simple. The particles should pass through. Atoms were thought to be like a soft cloud of charge, spread evenly through empty space, and the bullets would zip right through without much deflection. Most of them did exactly that, but some didn't. A few particles bounced straight back, almost directly toward the source. Rutherford described his reaction in a famous letter. He said it was as if you fired an artillery shell at tissue paper, and it bounced back and hit you. That moment changed everything. If particles were bouncing back, something dense and hard had to be stopping them. not a soft cloud, something compact, something concentrated. After careful analysis, Rutherford concluded that nearly all the mass of an atom was packed into a tiny central nucleus, thousands of times smaller than the atom itself. The rest of the atom was almost entirely empty space. This was confirmed physics. The nucleus was real, and the discovery created an immediate problem. If the atom was mostly empty space, the electrons had to be out there somewhere in that emptiness, moving around. The only model that made any physical sense was the one Rutherford himself proposed: electrons orbiting the nucleus like planets around the Sun. But as we've already seen, classical physics immediately predicted that model should fail. Orbiting electrons should radiate energy and collapse within 100 billionth of a second. Rutherford knew about this problem. He had no solution. He published his planetary model anyway, because at least the nucleus part was clearly right, and because something had to serve as the working picture until someone smarter figured out the electron half. That left a strange situation. Scientists had a confirmed discovery about the center of the atom, and a completely broken theory about everything outside it. The rest was a mystery. And the mystery came with stakes. If electrons weren't orbiting, what were they doing? They had to be somewhere. They had to be doing something. The electrical attraction between the negative electron and the positive nucleus had to be balanced somehow. Or the electron would fall inward, or fly off into space. There had to be a rule governing this, a law. Something that determined exactly where electrons lived and why they stayed there. Scientists searched for that rule inside classical physics and came up empty every time. The answer was going to require a completely different way of thinking about what a particle even is. It was going to require abandoning the idea that an electron is a tiny ball moving through space on a definite path. It was going to require treating the electron as something that classical physics didn't have a word for yet. And the first person to seriously suggest what that something might be wasn't even a professional physicist at the time he had the idea. He was a graduate student, writing his thesis, taking a gamble that his professors might reject outright. The problem was staring everyone in the face. Classical physics said electrons should spiral inward and destroy every atom in existence. But atoms were clearly not destroying themselves. Something had to be holding the whole system together. Niels Bohr's solution was audacious, in the most uncomfortable way possible. He didn't explain why electrons were stable. He just said they were, under certain conditions, and dared the evidence to prove him wrong. In 1913, Bohr published 3 papers that rewrote atomic physics. His central claim was simple: electrons could only orbit the nucleus at specific fixed distances. He called these allowed orbits. At these distances, and only at these distances, an electron would not radiate energy. It would not spiral. It would simply stay there, locked in a stable path, ignoring the classical physics that said it shouldn't be possible. Move to any other distance, the classical rules would take over and the electron would fall. Stay at one of the allowed orbits, the electron was fine, permanently stable, no explanation required. To understand why this felt strange to other physicists, imagine telling someone that a ball rolling down a hill will stop at certain exact heights for no reason and keep rolling at others. The stopping heights aren't explained. They just are. Accept it. That was Bohr's model. And yet, the predictions it made were extraordinary. Hydrogen atoms, when heated or electrically excited, release light in very specific colors. Not a rainbow of everything, just a handful of precise frequencies. Scientists had been cataloging those exact colors since the 1880s, without understanding why hydrogen chose those particular ones. Bohr's model explained them perfectly. When an electron absorbs a specific amount of energy, it jumps from a lower allowed orbit to a higher one. When it falls back down, it releases that same energy as a photon of light. Because the allowed orbits are fixed, the energy gaps between them are fixed, and fixed energy gaps mean fixed colors of light. Every single observed color in the hydrogen spectrum matched Bohr's math exactly. This was stunning. For the first time, someone had built a model of the atom that produced real, testable, correct predictions. Bohr wasn't just gesturing at an explanation. He was generating numbers that matched experiments down to the decimal. The Nobel Prize followed in 1922, but the triumph was fragile. Bohr's model worked beautifully for hydrogen, one electron orbiting one proton. The moment scientists tried to apply it to helium, the next element over with two electrons, the predictions broke down. The math stopped matching. The two electrons interacted with each other in ways Bohr's fixed orbit picture couldn't account for. And the deeper issue remained untouched. Bohr had simply declared that certain orbits were stable. He had given no reason why. His model was built on a rule without a foundation, a wall with no supports underneath it. It worked for one specific case and fell apart for everything more complicated. The question every serious physicist kept returning to was the same. Why those orbits? Why those distances? What physical principle was actually at work? The answer was hiding in a completely different field of physics. It had nothing to do with electrons yet. It was about light, and it involved a discovery so strange that even the scientists who made it couldn't fully believe it. The hydrogen atom is the simplest thing in chemistry. One proton in the center, one electron somewhere outside. That's it. No complications. Just two particles pulling on each other across a tiny gap. For this single case, Bohr's model was a triumph. The math matched, the predicted colors of light matched, the energy levels matched. Everything lined up. But the universe contains 92 naturally occurring elements. Hydrogen is just the first. The moment you move to element 2, helium, everything Bohr built begins to crack. Helium has 2 electrons. Those 2 electrons don't just interact with the nucleus, they interact with each other. They push against each other because both carry negative charge. Their movements affect each other constantly. The system is no longer 2 particles. It's 3, and 3-body problems in physics have never had clean, exact solutions. Bohr's model assumed electrons moved in fixed, independent circles. It gave each electron its own lane and told it to stay there. But real electrons in helium don't have independent lanes. They're tangled up with each other, pushing and pulling, shifting each other's energy levels in ways that Bohr's fixed orbits couldn't capture. Scientists ran the numbers. For hydrogen, Bohr's predictions were nearly perfect. For helium, they were off. For anything heavier than helium, the model produced results that didn't come close to matching experiments. Lithium, carbon, oxygen, iron, gold, all wrong. This wasn't a small error to be adjusted. The entire framework was breaking down. The model that felt so solid for hydrogen became useless as soon as chemistry got even slightly complicated. And chemistry is always complicated. The properties of every element, the way atoms bond together to form molecules, the shape of water, the structure of every drug, the behavior of every material humans have ever used, all of it depends on electrons doing things Bohr's model couldn't describe. There was something else missing too. Bohr's model made atoms sound mechanical. Click here, jump there, land in this orbit. The electron was still imagined as a tiny ball, a particle with a definite location at every moment, moving along a definite path. Classical intuition still held, but experiments were beginning to suggest that the electron wasn't behaving like a ball at all. Light had already caused trouble here. For decades, physicists had been forced to accept that light sometimes acted like a wave and sometimes like a particle, depending on the experiment. Nobody fully understood why. Nobody had a clean picture that made sense of both behaviors at once. And there was a young man in Paris who was beginning to wonder whether electrons might have the same split personality. If electrons could act like waves, then everything about how they behaved inside atoms would need to be rethought from scratch. The fixed orbits, the definite paths, the clean little diagram in the textbook, all of it would have to go. The idea was radical enough that even proposing it took courage. Because once you say an electron is a wave, you have to answer the obvious follow-up question. A wave of what? Paris, 1924. A 31-year-old man named Louis Victor de Broglie, the 7th Duke de Broglie, sat down to finish his doctoral thesis at the Sorbonne, one of the oldest universities in the world. De Broglie came from French nobility. His older brother Maurice was a respected physicist, and Louis had followed him into science after briefly studying history. He was quiet, thoughtful, and deeply bothered by a question that most people had already moved past. Light had two faces. Everyone knew light was a wave. It bent around corners, created interference patterns, traveled in ripples through space. Wave behavior, confirmed and measured for over a century. But in 1905, Albert Einstein showed that light also behaved like a stream of particles, packets of energy that hit surfaces and knocked electrons loose in a way that waves couldn't explain. He called these particles photons. The discovery eventually won him the Nobel Prize. So light was both a wave and a particle. Depending on the experiment you ran, you got a different answer. Physicists had mostly accepted this as a strange fact about light and moved on. De Broglie couldn't move on. He sat with the question and pushed it further. If light, which everyone had always thought of as a pure wave, could behave like a particle, why couldn't the reverse be true? Why couldn't matter, which everyone thought of as made of particles, behave like a wave? Specifically, why couldn't an electron? He wrote the idea into his thesis. Every moving particle, he proposed, has a wavelength. The wavelength depends on the particle's mass and speed. For heavy everyday objects like a baseball or a school bus, the wavelength is so incredibly small, it's impossible to detect. Completely irrelevant. But an electron is thousands of times lighter than even the lightest atom. Its wavelength falls into a range that's physically meaningful, physically real, potentially detectable. And de Broglie went further. He applied the wave idea directly to Bohr's mysterious allowed orbits. Bohr had simply declared that certain distances from the nucleus were stable, with no explanation. De Broglie showed that those exact distances were the ones where an electron's wave would close smoothly on itself, forming a stable loop. Every other distance caused the wave to clash with itself and cancel out. Bohr's unexplained rule suddenly had a physical reason. The allowed orbits were the only orbits where an electron's wave could survive. The thesis committee at the Sorbonne read de Broglie's work and felt deeply uncertain. The idea was too strange, too far outside anything they had seen before. One committee member reportedly sent the thesis to Einstein to ask whether it was brilliant or nonsense. Einstein wrote back that it was neither. He said it was more than an analogy, it was a real physical insight. The committee passed de Broglie, but passing the thesis was one thing. Accepting the idea as real physics required something more. It required an experiment that could catch an electron acting like a wave in the physical world, something you could measure, photograph, and hold up as proof. That experiment was already being planned, and when the results came in, they were impossible to argue with. The question seems simple. Light is a wave. Everyone agreed on that for 200 years. Then experiments showed it also behaves like a particle. Physicists accepted it, filed it under strange but true, and kept working. De Broglie just turned the question around. If something we thought was purely a wave can act like a particle, then something we thought was purely a particle might act like a wave. The logic is clean. The implication is enormous. And the history of light's dual nature is worth slowing down on because it's the foundation that de Broglie built his whole idea on. In the early 1900s, a puzzle emerged in physics labs. When light shines on certain metal surfaces, it knocks electrons loose. Simple enough. But the way it knocked them loose was wrong, according to wave theory. Wave theory predicted that brighter light should produce higher energy electrons. Frequency shouldn't matter. Intensity should rule. Experiments disagreed completely. Dim blue light knocked electrons loose. Bright red light knocked nothing, regardless of how powerful you made it. The energy of the electrons depended on the color of the light, meaning its frequency, not its brightness. Einstein explained this in 1905 with a simple but shocking idea. Light travels in discrete chunks of energy called photons. Each photon carries an amount of energy tied to its frequency. A single blue photon carries enough energy to eject an electron. A red photon, no matter how many you send, doesn't carry enough per packet. This explained the experiments perfectly. It also meant light was granular, chunky, particle-like. But light also created interference patterns when passed through narrow slits, exactly the behavior of waves spreading out and overlapping. Both descriptions were experimentally real. Light was both. De Broglie read all of this and asked the obvious next question. If the wave-particle division applies to light, why would it stop there? Why would nature draw a hard line between things we call light and things we call matter? The electron had always been called a particle. But what if that label was just a habit? What if every moving particle carries a wave with it? The wave de Broglie proposed wasn't a metaphor. He gave it a mathematical form. The wavelength of any particle equals a fundamental constant, called Planck's constant, divided by the particle's momentum. The heavier and faster something is, the shorter its wave, the lighter and slower, the longer. A baseball thrown at 60 miles per hour has a wavelength trillions of times smaller than a single proton. Completely unmeasurable. An electron moving inside an atom has a wavelength comparable to the size of the atom itself. That overlap is the key. It means wave behavior in an atom isn't a tiny correction. It's the dominant physics. It's everything. De Broglie's thesis said, stop thinking of the electron as a ball on a track. Start thinking of it as a wave wrapped around the nucleus, vibrating in patterns, stable only at certain frequencies. The idea was beautiful, it was logical, and it had to be tested. What came next was an experiment that neither of the scientists running it fully expected. In 1927, two American physicists named Clinton Davison and Lester Germer were working at a laboratory in New York with equipment that had nothing to do with de Broglie's theory. They were studying how electrons bounced off metal surfaces, standard lab work, no grand ambitions. Then an accident happened. Their vacuum tube broke. Air got in. The nickel target they were using oxidized. To clean it, they heated the metal to high temperatures, which accidentally caused the nickel to recrystallize into large, orderly atomic structures. When they resumed their experiment with the repaired equipment, the results were completely different from before. Instead of electrons bouncing off in random directions, the electrons were coming off the nickel surface in specific, organized angles, strong in some directions, almost nothing in others. Davison didn't immediately know what he was looking at. He brought his results to a conference in England that summer. There he heard about de Broglie's matter wave hypothesis for the first time. He sat in the audience and realized that the strange pattern he had measured back in his lab was exactly what you would expect if electrons were waves. Waves passing through a regular grid of atoms, like the crystal structure in nickel, create interference patterns. They bend and spread and overlap. Where two wave peaks meet, you get a strong signal. Where a peak meets a trough, they cancel and you get nothing. The exact angles where you detect strong signals depend on the wavelength of the wave and the spacing between the atoms in the crystal. Davison went home and ran the calculation. The wavelength he needed to explain his electron data matched perfectly with the wavelength de Broglie's formula predicted for electrons at that speed. The match was exact. Davison and Germer published their results, confirming the wave nature of electrons through direct experiment. At almost the same time, a British physicist named George Paget Thomson independently fired electrons through thin metal films and observed the same interference rings, further confirmation from a completely different setup. The electron was a wave. Confirmed. This wasn't a theory anymore. You could photograph the interference pattern. It was right there in the data, organized and clear, the unmistakable fingerprint of wave behavior. The implications arrived quickly and hit hard. If electrons behave like waves, then inside an atom, the electron isn't a tiny ball traveling a fixed circular path. It's spread out, vibrating, existing in a wave-like pattern all around the nucleus simultaneously. The clean diagram in the textbook, the neat little circles with arrows, every single one of those arrows was pointing at something that didn't exist. A new picture was needed. One built on waves, on mathematics, on probability. Fortunately, there was already a physicist working on exactly that. He had been building the equation that would replace Bohr's model entirely, and he would publish it within the same year that Davison and Germer ran their experiment. His equation didn't tell you where the electron was. It told you where it might be. And that distinction between knowing and might be turned out to be the most important distinction in the history of physics. In 1926, Erwin Schrödinger published a wave equation. On the surface, this sounds like a routine event in physics. Equations get published constantly. Most are forgotten within years. A handful reshape entire fields. Schrödinger's equation reshaped everything. He built it on de Broglie's foundation. If electrons are waves, then the behavior of those waves inside an atom should follow the same kind of mathematics that describes any other wave, the same logic that governs sound vibrating in a pipe or light bouncing between mirrors. Schrödinger wrote down the equation that described how an electron's wave evolves through space and time. He applied it to the hydrogen atom. The results came out clean. Where Bohr had to manually declare which orbits were allowed, Schrödinger's equation generated the allowed energy levels automatically. They fell out of the math, the way answers fall out when you solve any equation correctly. The equation didn't need Bohr's unexplained rule. The allowed states were built into the wave mathematics itself. And the equation worked for more than just hydrogen. It worked for helium, for carbon, for every atom scientists tested it against, for molecules, for chemical reactions. The equation was universal in a way Bohr's model had never been. But there was something deeply strange buried in what the equation produced. The solutions to Schrödinger's equation are called wave functions. A wave function is a mathematical object that describes the electron state completely. It varies across space, higher in some regions, lower or zero in others, oscillating in complex patterns depending on the atom and the energy level. Here is the strange part. The wave function itself doesn't tell you where the electron is. To get something physically meaningful, you have to square the wave function, multiply it by itself. The result gives you a number for every point in space, and that number is the probability of finding the electron at that point if you were to measure it. High number, likely to find the electron here. Low number, unlikely. 0, impossible. The electron doesn't have a location until you look for it. Before measurement, the wave function spreads through space, a three-dimensional landscape of probabilities, all of them simultaneously real. This interpretation was developed by a physicist named Max Born, and it came with an uncomfortable conclusion. The electron isn't hiding somewhere definite, waiting for us to find it. It genuinely exists as a spread-out probability distribution. There is no hidden location. The uncertainty is built into the electron itself. This was so philosophically disturbing that even Schrödinger himself struggled with it. He later invented a famous thought experiment involving a cat in a box to show how strange this interpretation became when pushed to larger scales. The cat thought experiment was meant as a critique. It became one of the most famous illustrations in all of physics. Schrödinger won the Nobel Prize in Physics in 1933 for his wave equation, but the equation raised a question that it couldn't answer on its own. If the electron exists as a probability spread through space, what happens to all that spread when you actually measure it? The moment you detect the electron somewhere, the probability cloud vanishes and the electron snaps to a single point. That process had a name, and explaining it required a principle that another physicist had already written down, one that proved the uncertainty wasn't just a gap in our knowledge. It was the shape of reality itself. Most people learn about equations in math class and imagine them as things you solve to get one clean answer. Schrödinger's wave function doesn't work that way. The wave function is a description of everything about the electron's state at once. Think of it as a map, a detailed three-dimensional map that covers all of space around the nucleus, assigning a value to every single point. Those values can be positive or nearly zero. They oscillate in complex shapes depending on how much energy the electron carries and how it's arranged around the nucleus. The map itself, though, isn't something you can directly observe. You can't measure the wave function directly. There's no instrument that reads it off like a thermometer reads temperature. To get something real, something you can actually compare to an experiment, you square the wave function. Take the value at each point in space, multiply it by itself. Now you have a new map, one where every number is positive, because squaring removes the negative values. This new map is called the probability density. It tells you how likely you are to find the electron at each location in space if you run a measurement at that moment. Regions where the probability density is high, the electron shows up there often. Regions where it approaches zero, the electron almost never appears there. Regions where it equals exactly zero, the electron is never found there. These are called nodes. They're real and precise, and they matter enormously for how atoms interact with each other. Picture a heat map of a city, like the ones that show you where most people walk during a day. Hot zones mean lots of people. Empty zones mean nobody goes there. The wave function squared is the same kind of map, but for where an electron lives. Now here's the crucial part. This isn't a map of where we think the electron probably is, because we don't have good enough instruments. The probability is fundamental. The electron genuinely has no single definite location before measurement. The wave function spread across space is its actual physical state. A physicist named Max Born proposed this interpretation in 1926, the same year Schrödinger published the equation. Born said the wave function squared gives you the probability of finding the electron. Full stop. The electron exists as a cloud of probabilities, and when you make a measurement, one outcome from that cloud becomes real. This was hard for everyone to accept. It still is. Einstein never fully accepted it. He spent years trying to show that the probability description had to be incomplete, that a more exact hidden description must exist. Underneath, he and Bohr argued about this at famous physics conferences, two towering intellects on opposite sides of a fundamental question about the nature of reality. Experiments run decade after decade kept siding with Born's interpretation. The wave function is not incomplete. The probability is the reality. The electron is a smear of possibilities until you force it to pick one by measuring it. And once you accept that, the picture of the electron inside an atom changes completely. There's no orbit, no path, no tiny balls circling the nucleus in a ring. There's a cloud. A specific mathematically defined shape, different shapes for different energy levels. And those shapes have names. What they look like next is going to surprise you. The statement feels wrong the moment you hear it. Before you measure an electron, it exists in multiple places at once. Every instinct pushes back against this. Objects are somewhere. A ball is either here or there. You either find it or you don't. The idea that something could genuinely be in multiple places simultaneously, without any hidden trick, without any missing information, breaks every intuition built by living in the everyday world. And yet this is confirmed physics. The proof doesn't come from philosophy. It comes from double-slit experiments, one of the most repeated and documented experiments in all of science. Here's the setup. You fire electrons one at a time through two narrow slits cut into a barrier. Behind the barrier is a screen that records where each electron lands. If electrons were simple particles, like tiny bullets, you'd expect two clusters on the screen, one behind each slit. Each bullet either goes through the left slit or the right slit, never both. Instead, you get an interference pattern, dozens of alternating bands, bright and dark, spread across the screen, the exact pattern you'd see if you sent water waves through two slits and let them spread and overlap on the other side. One electron going through two slits simultaneously, interfering with itself. Now here is where it gets stranger. If you set up a detector to watch which slit the electron actually goes through, the interference pattern disappears. The moment you measure which path the electron took, it picks one. It stops being in two places at once. The two-band particle pattern returns. The act of measuring the path collapses the electron from a spread-out wave of possibilities into a single definite location. This is called wave function collapse. It's confirmed by experiment. Every version of this test, run in labs around the world for decades, gives the same result. The electron doesn't secretly go through one slit while we're not looking. The math and the experiments both show it genuinely passes through both simultaneously, as long as no measurement is made. The moment measurement happens, all of that simultaneous existence collapses to one outcome. This isn't a weird edge case limited to special lab conditions. Inside every atom, electrons exist as spread-out wave functions all the time. The probability cloud isn't a loose description. It's the actual physical state of the electron. The cloud is real. The spread is real. And the collapse happens every time any physical interaction forces the electron to declare a location. That means inside every atom in your body, in the metal of your phone, in the air molecules around you, electrons are existing in this spread-out, probabilistic state continuously. The solid, definite world you see and touch is built from a foundation of quantum fuzziness held in place by mathematical rules. The image of electrons as tiny planets circling a nucleus made atoms feel solid and mechanical. The real picture makes them feel almost like patterns of potential, shapes held together by the rules of probability. And there's a physicist who made this even stranger. He proved that the uncertainty isn't something that can ever be overcome by better technology or sharper measurements. He proved it's built into the fabric of reality at the deepest level. His name was Werner Heisenberg, and his discovery is about to change the way you see every object in the world. Werner Heisenberg was 25 years old when he figured it out. In 1927, working in Copenhagen under Niels Bohr, Heisenberg was pushing on the edges of what quantum mechanics allowed. He kept running into the same wall. Every time he tried to make the math describe an electron with both a precise location and a precise speed, the equations broke down. At first, he thought this was a problem with the theory, a gap that needed fixing. Then he realized the gap was intentional. The gap was reality. He published the uncertainty principle in 1927. The statement is simple. The more precisely you know where a particle is, the less precisely you can know how fast it's moving and in what direction. And the more precisely you know its speed and direction, the less you can know its location. The two pieces of information are permanently linked. Pin one down tightly, and the other becomes blurry, always, by a fixed mathematical minimum. This gets mistaken for a measurement problem. People assume Heisenberg was saying our instruments disturb the electron when we try to measure it, like trying to find a ball in a dark room and bumping into furniture on the way. That's not what he was saying. The uncertainty is not about instruments. It is not about interference from the measuring process. It is a fact about the electron itself before any measurement happens. The electron does not simultaneously have a precise location and a precise momentum. These two properties are fundamentally incompatible. They cannot both be sharp at the same time for any particle anywhere in the universe, ever. Position and momentum are woven together in such a way that sharpening one automatically blurs the other. The math is exact. The product of the uncertainty in position and the uncertainty in momentum can never fall below a specific minimum value, set by Planck's constant, one of the fundamental numbers of the universe. For everyday objects, this limit is so tiny it's completely irrelevant. A baseball, a car, a person. None of them are affected in any measurable way, but an electron is roughly 900 times lighter than even the lightest atom. At that scale, the uncertainty is enormous compared to the size of the electron's world. The uncertainty doesn't sit quietly in the background. It dominates everything. Inside an atom, the electron's location is uncertain across a volume comparable to the entire atom. Its momentum is uncertain across a real range of values. These are not failures of knowledge. They are the true state of the electron. This principle demolished the last hope of saving the classical orbiting picture. For an electron to follow a fixed circular orbit, you would need to know both its exact location on the circle and its exact speed at every moment. That combination of information is precisely what the uncertainty principle forbids. Classical orbits require exactly the kind of simultaneous precision that nature refuses to provide. The orbiting electron isn't just experimentally unsupported, it's logically impossible under the laws of the universe. And Heisenberg's principle does something else, something even more surprising. It answers the question that started this whole story. Why don't electrons fall into the nucleus? The uncertainty principle is the reason atoms are stable. And the way it works is stranger than you'd expect. The electron is negatively charged. The nucleus is positively charged. Opposite charges attract. So why doesn't the electron fall straight into the nucleus and stay there? Classical physics had no answer to this. Quantum mechanics does. Start with the uncertainty principle and follow the logic. Imagine you tried to trap an electron inside the nucleus. The nucleus is tiny, roughly 100,000 times smaller in diameter than the full atom. If the electron were sitting inside the nucleus, its position would be known with extraordinary precision, confined to that tiny volume. The uncertainty principle says, pin down the position sharply, and the momentum becomes wildly uncertain. Wild uncertainty in momentum means the electron's speed and direction can take on an enormous range of values. A huge uncertainty in momentum corresponds to an enormous average kinetic energy, the energy of motion. In practice, the electron would be moving so violently that the electrical pull of the nucleus couldn't hold it. It would blast outward with far more energy than the nucleus could capture. The tighter you squeeze the electron toward the nucleus, the more violently it resists. So the electron settles into a compromise. It spreads out enough that its position uncertainty is large, which keeps its momentum uncertainty manageable, which keeps its kinetic energy at a level the nucleus can balance with electrical attraction. This natural balance between the pull of the nucleus and the quantum push of confinement defines the size of the atom. The atom isn't held together by classical gravity or simple electrical attraction alone. It's held together by the geometry of quantum uncertainty. The electron's probability cloud settles at the distance where these forces reach equilibrium. And the energy at that equilibrium is the lowest possible energy the electron can have in that atom. Physicists call this the ground state. An electron in the ground state can't lose energy and fall lower. There's nowhere lower to go. The ground state is the floor. Any attempt to push the electron closer just drives up its energy and shoots it back out. This is why atoms don't collapse. This is why matter is stable. The uncertainty principle sets a lower limit on how compressed an electron's world can be, and that limit turns out to be roughly the size of an atom. Every atom you've ever touched, every molecule your body is made of, every material humans have ever used, all of it owes its existence to a quantum rule that says the universe will not allow you to know too much about a particle at once. And once physicists understood this, they could finally ask a question nobody had been able to answer properly before. If the electron isn't circling the nucleus in a fixed orbit, what does its actual three-dimensional home look like? The answer comes in several forms. Each one is precise, mathematically derived, and experimentally confirmed. And the simplest one looks almost familiar, until you look closely enough to realize it's hiding a secret that should not be physically possible. The word orbital sounds like orbit. That similarity is a trap. An orbit is a path, a specific track through space, like a highway in the sky. You can draw it as a line. You can say the object is here at this moment and there at the next. An orbital is a region, a volume of space defined by probability. There is no path inside it. There is no track. There's just a three-dimensional zone where the electron is likely to be found, calculated from the wave function Schrödinger's equation produces. Here's how physicists define it precisely. Take the wave function for an electron in a particular energy state. Square it to get the probability density across all of space. Now, draw a surface around the nucleus that encloses 90% of that total probability. Everything inside that surface is the orbital. 90% means there's still a 10% chance of finding the electron somewhere outside that surface on any given measurement. The orbital doesn't have a hard edge. The probability never drops to exactly zero at any finite distance. It fades. It thins out. But theoretically, an electron in a hydrogen atom has a non-zero probability of being detected anywhere in the universe. Practically, the probability becomes so vanishingly small outside the orbital region that it's irrelevant. Inside the orbital, the probability is high. Outside, it's low. The surface drawn at 90% is a convenient way to visualize where the electron actually spends its time. Now, here's what makes the orbital more than just a fuzzy substitute for an orbit. Different energy levels produce orbitals with completely different shapes. These shapes are exact. They're not estimates. They're the direct mathematical output of Schrödinger's equation, as precise as any geometric calculation. Every atom in the universe organizes its electrons into these shapes. The shapes determine how atoms interact with each other. They determine which atoms can bond and which can't, which molecules form and which don't, which materials are solid and which are gas, which compounds are stable, and which react. The shapes of electron orbitals are the geometry of chemistry. There are 4 basic types, labeled with the letters S, P, D, and F. These labels originally came from spectroscopy, the study of light emitted by atoms, where scientists described certain spectral lines as sharp, principal, diffuse, or fundamental before anyone knew what caused them. The letters stuck even after the wave functions explained everything. Each type has its own geometry. Each geometry arises from a specific mathematical solution to Schrödinger's equation, and each one holds only a limited number of electrons, governed by a rule we'll get to shortly. The simplest shape, the s orbital, looks like a sphere. Smooth, round, centered on the nucleus, the electron could show up anywhere on the surface of that sphere with roughly equal probability. But the s orbital has a secret hiding right at its center that classical physics said was impossible. The s orbital is the first home electrons settle into. Every atom starts filling electrons from the lowest energy state, and that lowest state is the first s orbital. Hydrogen's single electron lives here. So do the inner electrons of every heavier element. The shape is a sphere, three-dimensional, centered on the nucleus, symmetrical in every direction. Imagine a fuzzy ball of probability surrounding the nucleus, densest in the middle and fading outward as you move away. The electron is most likely to be found at a specific distance from the nucleus, a distance that defines roughly where the surface of the probability ball sits. This part is relatively easy to picture, but the probability doesn't start at zero right at the nucleus and build up from there. The wave function passes through the nucleus itself. At the very center, at the location where the proton sits, the probability density of finding the electron is small but real. The number is above zero. There is a genuine, non-zero chance that a measurement would find the electron inside the atomic nucleus. The electron cloud passes straight through the center of the atom. This happens in real chemistry. The phenomenon is called electron capture, and it's how certain unstable atoms decay. A proton in the nucleus can absorb an electron from the innermost s orbital, converting the proton into a neutron and releasing a neutrino. This isn't a theoretical edge case. It happens in atoms like potassium-40, which is in your body right now, and it's measurable and well documented. The electron has to be genuinely present at the nucleus for this interaction to occur, and quantum mechanics confirms that it is. Classical orbital physics had no room for this. In Bohr's model, the innermost allowed orbit sat at a fixed distance from the nucleus. The electron stayed on its track. It never went closer. It certainly never went inside. In quantum mechanics, the electron has no track. Its probability cloud fills a volume. That volume includes the interior of the nucleus. The electron isn't circling the nucleus from the outside. It's a smear of probability that exists throughout the space around and including the nucleus. This is a real difference. The difference between orbiting around something and existing throughout the space it occupies is not a minor adjustment to the picture. It's a completely different kind of relationship between the electron and the nucleus. And the s orbital is the simplest case. The higher energy orbitals take shapes that make the sphere look straightforward by comparison. The next type, the p orbital, looks nothing like a sphere. It comes in 3 versions, each pointing along a different axis in space. And right at the center of every p orbital, exactly where the nucleus sits, there is a zone where the electron is absolutely, completely, mathematically forbidden to exist. And yet the electron is somehow on both sides of it at the same time. The p orbital looks like a dumbbell, 2 lobes, one on each side of the nucleus, pointing outward along an axis. The electron lives in those lobes. When you run a measurement, you find it in one lobe or the other, somewhere in that double bubble shape of probability. Picture a figure 8 lying on its side, then give it depth and 3 dimensions. That's the shape, 2 rounded regions, connected through the nucleus, the electron's probability spread across both. Now here's the detail that should bother you. Right at the center of the p orbital, exactly where the 2 lobes meet, where the nucleus sits, the probability density drops to exactly 0. This point is called a node. The wave function equals 0 there. Squaring 0 gives 0. The probability of finding the electron at the node is precisely mathematically 0. The electron cannot be there. The node is a zone of absolute impossibility for the electron, and the electron exists in both lobes simultaneously. Let that picture sit for a moment. The electron occupies the left lobe. It also occupies the right lobe. Between the 2 lobes, at the exact center, there's a region it can never occupy. There is no path from left lobe to right lobe that avoids the node, because the node is literally the meeting point of the 2 lobes, the only connection between them. In classical physics, this is impossible. A ball can't be in 2 separate places if there's an uncrossable barrier between them. It would have to pass through the barrier to get from one side to the other, but the electron isn't a ball. It's a wave. A wave can have nodes, places where the wave amplitude is exactly 0, while simultaneously being active on both sides of those nodes. Sound waves do this. Water waves do this. A standing wave on a guitar string has nodes, points that don't move at all, while the rest of the string vibrates actively on both sides. The wave exists on both sides of the node without ever needing to pass through it. The electron behaves the same way. It's a standing wave around the nucleus. The node isn't a wall. It's just a point where the wave function hits 0, the same way a vibrating guitar string has still points along its length. This is confirmed physics. Scanning tunneling microscopes have imaged p orbitals. Directly, the 2 lobes are visible. The shape matches the mathematical prediction exactly. The p orbital comes in 3 versions. One points left and right, one points up and down. 1 points forward and back. All three exist simultaneously in any atom with electrons at that energy level, each oriented along a different axis, each with its own node at the center. But the p orbital is still relatively simple compared to what comes next. The d and f orbitals are shapes so geometrically strange that even physicists who work with them daily occasionally pause to appreciate how odd they are. And they're completely real, confirmed by the same microscopes that imaged the p orbital. If the s orbital is a sphere and the p orbital is a dumbbell, then the d orbitals are something that looks like it was designed to be deliberately difficult to describe. There are 5 d orbitals, and most of them have 4 lobes arranged in a cloverleaf pattern around the nucleus. 2 lobes pointing up and down, 2 pointing left and right, all 4 surrounding a central nucleus, with nodes separating each lobe from the others. One of the 5 d orbitals looks completely different from the others. Instead of a cloverleaf, it has 2 lobes pointing up and down along a single axis, with a donut-shaped ring of probability wrapping around the middle at the equator. A dumbbell with a life preserver around its waist, this orbital exists in real atoms. It's not an approximation or a simplified teaching tool. The f orbitals push even further. There are 7 of them. Their shapes are complex enough that chemists and physicists typically describe them using mathematical notation rather than visual language. Some look like 2 interlocking 4-leaf clovers. Some have lobes pointing in multiple directions, simultaneously with multiple nodes cutting through them. They're accurate solutions to Schrödinger's equation, derived from the math, consistent with every experiment ever run on atoms that contain them. And here's why this matters beyond geometry class. Scanning tunneling microscopes, invented in the 1980s, can map the electric charge distribution around individual atoms on a surface. When researchers used these microscopes to image atoms with d and f orbital electrons, the images that came back matched the quantum mechanical orbital shapes to a degree that removed any remaining doubt. The fuzzy lobes, the dark nodes, the exact orientations, all of it present in the physical world, exactly where the equation said it would be. Quantum mechanics predicted the shapes of electron clouds before anyone had the technology to see them directly. The math was written in the 1920s. The microscopes arrived 60 years later. The images matched. There's a particular image that circulates in physics textbooks, a grid of hydrogen atom orbital shapes mapped by scanning tunneling microscopes, rows and columns of electron probability clouds captured at different energy levels. Looking at it is a strange experience. You're seeing something that should feel abstract, a probability distribution, a mathematical solution, and it's right there as a visible, photographable physical reality. The d and f orbitals also determine the behavior of entire sections of the periodic table. The transition metals, the elements in the middle of the periodic table including iron, copper, gold and nickel, get their chemical properties almost entirely from their d orbital electrons. The lanthanides and actinides, including uranium, get theirs from f orbital electrons. The color of copper, the magnetism of iron, the chemical stubbornness of gold. All of these properties trace back to the specific shapes of d and f orbital wave functions. Every material property you've ever interacted with is a consequence of orbital geometry. The shape of an electron cloud, derived from a wave equation written in 1926, controls the behavior of every element in the physical world, and determining which electrons fill which orbitals, and in what order, required a discovery that came from an experiment nobody had planned on. A physicist needed an address system for electrons, and the rule that governs that system turns out to be the reason solid matter is solid at all. Every electron in every atom has an address, not a physical address, a quantum address, a set of 4 numbers that together describe everything about where that electron lives and how it behaves. Change any one of the 4 numbers, and you're describing a completely different electron in a completely different state. Physicists call these the 4 quantum numbers. The first number is called the principal quantum number. It describes the electron's energy level, essentially which shell it occupies, how far out from the nucleus its probability cloud sits on average. The lowest energy level is 1. Higher numbers mean higher energy and greater average distance from the nucleus. An electron at level 1 is hugging the nucleus. An electron at level 4 is far out, in a much larger cloud, held more loosely. The second number describes the shape of the orbital. 0 gives you an s orbital, the sphere. 1 gives you a p orbital, the dumbbell. 2 gives you a d orbital, the cloverleaf. 3 gives you an f orbital, the complex multi-lobed shapes from the last chapter. This number tells you which type of probability cloud the electron inhabits. The third number describes orientation. A p orbital can point along 3 different axes in space. A d orbital has 5 different orientations. The third quantum number specifies exactly which direction the orbital is pointing. It tells you the orbital's position in 3-dimensional space relative to other orbitals in the same atom. The fourth number is spin. Every electron behaves as if it has an intrinsic magnetic property that can point in one of exactly 2 directions. Physicists call these spin up and spin down, assigned values of positive 1/2 and negative 1/2. The fourth number tells you which of the 2 spin states the electron is in. These 4 numbers together form a complete description, an electron's entire quantum identity, compressed into 4 values. Now comes the rule. In 1925, Austrian physicist Wolfgang Pauli stated what became one of the most powerful principles in all of science. No 2 electrons in the same atom can share the same set of all 4 quantum numbers simultaneously. Every electron gets a unique address, no duplicates, no exceptions. Ever. This sounds like a bookkeeping rule. It feels like something administrative, like a regulation about filing forms. But the consequences are staggering. Because of this rule, electrons cannot all pile into the lowest energy state. The first energy level fills up with just 2 electrons, 1 spin up and 1 spin down, both sharing the first s orbital. Once those 2 spots are taken, a third electron has no choice. It must go to the next energy level. The 4th electron joins it. When that level fills, the next electron climbs higher still. This forced stacking, electrons building upward through energy levels because every lower slot is already claimed, is why different elements have different numbers of electrons at different energy levels. Different arrangements of electrons at different energy levels produce different chemical behaviors. Different chemical behaviors are what make each element unique. Carbon, oxygen, sodium, chlorine, gold. Every element on the periodic table has a distinct personality because of the specific way its electrons are forced to stack, and that stacking is forced by Pauli's rule. The entire periodic table, 118 elements each with its own character, is a consequence of 4 quantum numbers and 1 rule about uniqueness. And the rule's most important effect isn't even in chemistry. It's in the fact that you can touch things. Put your hand on a table. You feel resistance. The table pushes back. It feels solid. This seems obvious, something you've experienced 10,000 times without thinking about it. But why does the table push back? The atoms in your hand and the atoms in the table never actually touch. Atoms are mostly empty space. The electrons in your hand's atoms and the electrons in the table's atoms never make contact in any classical sense. What you feel isn't solid surfaces pressing against each other. What you feel is the Pauli exclusion principle. When the electron clouds of your hand's atoms get close to the electron clouds of the table's atoms, the electrons from both sides would need to share the same region of space. But sharing the same region means sharing the same quantum numbers. And Pauli's rule forbids that absolutely. The electrons resist being forced into the same quantum state. That resistance manifests as a repulsive force, a real physical push, the force that stops your hand from passing through the table. Physicists call this electron degeneracy pressure, though the everyday version happens whenever any 2 objects are pressed together. The solidity of every material you have ever touched, is a direct consequence of electrons refusing to share quantum states. Wood is solid because of Pauli. Metal is solid because of Pauli. The ground beneath your feet holds you up because of Pauli. Now extend this to chemistry. The periodic table has a specific structure. Elements in the same column share similar chemical properties. Lithium, sodium, and potassium all react violently with water. Helium, neon, and argon barely react with anything. Fluorine and chlorine both grab electrons aggressively from other atoms. These patterns arise from how electrons stack into quantum states. When an atom has one electron in its outermost shell, that electron is easy to give away. The atom wants to shed it. Elements like this are highly reactive metals. When an atom's outermost shell is completely full, all available quantum states occupied, the atom has no tendency to react at all. Elements like this are the noble gases. Every chemical property, every reaction, every bond, every material traces back to how many electrons an atom has, how they're stacked into quantum states, and how many empty spots remain in the outermost shell. Pauli's rule determines the stacking. The stacking determines the chemistry. The chemistry determines the physical world. And one physicist pushed even further. He wanted to know why electrons in the same orbital had to have opposite spins. Why exactly 2 per orbital? Why not 3? Why not 1? The answer came from an experiment involving magnets, silver atoms, and a result that should have been impossible. And once you understand what that experiment found, you'll never think about the word spin the same way again. The word spin is misleading. It sounds like rotation, like a top twirling on a table or a planet turning on its axis. When physicists say an electron has spin, the image that naturally forms is a tiny sphere rotating around its own center. That image is wrong. And the reason it's wrong is one of the strangest corners of quantum mechanics. If an electron were a real spinning ball, you could calculate how fast its surface would need to move to produce the magnetic effects that spin actually causes. Physicists ran that calculation. The result, the surface of the electron would need to move faster than the speed of light. The speed of light is the absolute speed limit of the universe. Nothing with mass can reach it, let alone exceed it. So an electron physically spinning like a top is ruled out completely, not as a practical limitation, but as a logical impossibility under the laws of physics. Spin is real. The magnetic effects it produces are real and measurable, but spin has no classical equivalent. It's a purely quantum property, one that the mathematics of quantum mechanics requires, and that experiments confirm, but that cannot be visualized as any kind of rotation in physical space. The best description physicists have is this: spin is an intrinsic form of angular momentum built into every electron by the structure of the universe. It's as fundamental to what an electron is as its charge or its mass. You cannot separate it out, you cannot turn it off. Every electron has it, always, with no mechanism producing it that we can point to and describe in classical terms. And spin only comes in 2 flavors. Every electron is either spin up or spin down. These labels represent 2 possible orientations of the electron's intrinsic magnetic moment relative to an external magnetic field. The values are positive 1/2 and negative 1/2 in the units physicists use. No other values are possible. You will never find an electron with a spin of 0 or 1, or any fraction between the 2 allowed states. This is not a limitation of measurement, it's a fundamental feature of the electron's quantum nature. The universe has decided that this particular property comes in exactly 2 discrete options, and there are no in-between states available. This matters enormously for the Pauli exclusion principle, because spin provides the 4th quantum number, and that 4th number is what allows 2 electrons to share the same orbital. 2 electrons can occupy the same s orbital if and only if they have opposite spins. 1 spin up, 1 spin down. Their quantum addresses differ by that final number, so the Pauli rule is satisfied. Add a 3rd electron to the same orbital, and there's no remaining spin value it could have. both options are taken. The orbital is full. This is why every orbital holds exactly 2 electrons. The math of spin demands it. And the proof that spin is real, that it genuinely exists as a physical property and not just a mathematical convenience, came from an experiment that produced results so clean and stark they were impossible to argue with. In 1922, 2 German physicists named Otto Stern and Walther Gerlach ran an experiment they expected to be straightforward. They heated silver atoms in an oven until the atoms were moving fast enough to form a beam. Then they sent that beam through a region of space with a strong magnetic field that was stronger on one side than the other. A non-uniform field, deliberately uneven. Classical physics predicted what should happen. Silver atoms have a magnetic moment because of their electrons. A non-uniform magnetic field should pull on that magnetic moment and deflect the atoms as they fly through. But because the magnetic moments of the silver atoms should be oriented randomly, pointing in all directions like compass needles, scattered at random angles, the deflections should also be spread across a continuous range. The atoms should paint a smeared vertical stripe on the detector plate behind the magnet. Instead, they got 2 spots, 2 distinct bands, one above the center, one below. Nothing in between. The beam had split into exactly 2 separate streams. There were only 2 possible outcomes, separated by a gap, with nothing landing in between. Classical physics had no explanation for this. A continuously variable magnetic moment should produce a continuous smear. 2 discrete spots meant the magnetic moment could only point in one of 2 directions. Full stop. No intermediate angles allowed. This was the experimental proof that quantum spin is real and quantized. Silver's outermost electron determines its magnetic behavior. That electron's spin can only be in one of 2 states. When the non-uniform field pushes on it, the push is either up or down. Never sideways, never diagonal, never anything in between. The atom deflects up or deflects down, and the 2 groups land in 2 separate spots on the detector. The gap between the spots is physical proof that something in the electron is fundamentally binary. 2 options, no others. Later experiments removed all ambiguity. When physicists repeated the Stern-Gerlach setup with individual electrons instead of silver atoms, passing each electron through the magnetic field one at a time, each electron went one way or the other, never both. Never somewhere in the middle. Measure an electron's spin along one axis, and you get spin up or spin down with some probability for each outcome, determined by the electron's quantum state. Measure it again immediately after along the same axis, and you always get the same answer. But measure it along a different axis after the first measurement, and the probabilities reset. The spin doesn't have a fixed 3-dimensional orientation. It has a definite value only along whatever axis you choose to measure. This is deeply strange and deeply confirmed. Spin is real. Spin is binary for electrons, and the existence of spin, combined with Pauli's rule, determines which electrons can share which orbitals, and therefore which atoms, are chemically active and which are stable. And spin has one more consequence that connects to everyday experience in the most vivid way possible. It's the reason neon signs glow pink, and why different gases produce different colors of light when electricity passes through them. Walk past a neon sign at night and look at it directly. That pink-red glow isn't a paint or a filter. The glass tube is filled with neon gas. An electric current runs through it, and the color you see is a direct readout of the quantum structure inside every neon atom. Here's what's happening. When an electric current passes through the neon gas, it gives energy to the electrons in neon atoms. Those electrons absorb the energy and jump to higher quantum states, higher energy levels, higher orbitals further from the nucleus. But electrons don't stay in high energy states. They fall back down. When an electron drops from a higher energy state to a lower one, it releases the energy difference as a photon, a particle of light. The frequency of that photon, which determines its color, is set exactly by the energy gap between the two states. And here's the key part. The allowed energy levels in neon are fixed. Schrödinger's equation, applied to the neon atom, gives a specific set of allowed states. No electron can sit between two levels. The levels are quantized discrete, like the rungs of a ladder with no space between them. You can stand on rung 1 or rung 2, never on the air in between. So the energy gaps between levels are fixed, and fixed energy gaps mean fixed photon frequencies, and fixed frequencies mean fixed colors. Neon emits several specific frequencies of light when its electrons fall between particular levels. The combination of those specific frequencies, weighted by how often each transition happens, produces the distinctive reddish-pink color associated with neon. Fill the tube with a different gas and the color changes completely, because each element has its own unique set of energy levels and its own unique set of allowed transitions. Mercury vapor glows blue-green, argon glows blue to violet, helium glows peach-orange, hydrogen glows in a pinkish purple. Every color from every discharge tube is a direct fingerprint of that element's quantum orbital structure. This is the same effect Bohr used to build his original model. The hydrogen emission spectrum, those specific colors of light hydrogen produces, matched his calculations because the allowed energy levels produced fixed gaps. The gaps matched the colors. The model worked for hydrogen because hydrogen's spectrum is simple, just a single electron with a handful of allowed transitions. The full quantum picture, built on Schrödinger's equation and orbital wave functions, extends this to every element in the periodic table. But the neon sign does more than just glow. It shows something about the nature of electron energy that runs deeper than just color. Electrons don't gradually drift between energy levels. They don't slowly gain speed or slowly lose it like a car braking. They jump instantly. The electron is in one state, then it's in another, with no time spent in between. Why? Because electron energy levels in atoms aren't steps on a gentle slope. They're something more fundamental. They're standing waves, and standing waves obey a rule that is both simple and absolute. Pluck a guitar string. It vibrates. The vibration produces a sound, and the frequencies it produces aren't random. A guitar string fixed at both ends can only vibrate at certain specific frequencies. The fundamental, which is one full wave fitting between the two fixed ends, the second harmonic, 2 waves, the third, 3. Each harmonic is a standing wave, a pattern that sustains itself because the wave fits perfectly between the boundaries. Try to vibrate the string at a frequency that doesn't fit. The wave cancels itself. It doesn't sustain. The only stable vibrations are the ones that work with the geometry. This is exactly what happens with electrons inside atoms. De Broglie showed that electrons have wave properties. Schrödinger turned that into a full equation. The solutions to that equation around a nucleus are the wave functions we've been discussing. And those solutions are standing waves. The electron's wave wraps around the nucleus. For the wave to survive, it has to close smoothly on itself. The wave pattern has to fit the geometry, the same way a guitar string's vibration has to fit the length of the string. Only certain wave patterns fit. Those are the allowed energy states. Every other possible wave pattern produces a wave that clashes with itself and cancels out. It doesn't sustain. It can't exist. This is why electrons are only found at specific energy levels. The levels aren't arbitrary rules or unexplained declarations like Bohr proposed. They're the only frequencies at which the electron's wave can sustain itself as a stable pattern around the nucleus. And here's the consequence that changes everything about how you picture electron energy. A standing wave exists, or it doesn't. There's no halfway vibration. A guitar string is either vibrating in a stable harmonic, or it isn't. You can't have half a harmonic. The vibration doesn't gradually reduce to nothing. It either sustains, or it collapses. The same applies to the electron. An electron in a stable energy state is a standing wave. It doesn't lose energy gradually. It doesn't slowly decay toward the nucleus like the classical picture predicted. The standing wave simply persists, permanently, as long as nothing disturbs it. When something does disturb it, like a passing photon with exactly the right energy, the electron absorbs that energy and instantly reorganizes into the standing wave pattern for the next higher energy level. When it falls back, it releases the energy and instantly drops to the lower standing wave. The transition is sudden because there's no intermediate state available. The wave either fits a pattern or it doesn't. This is why the classical atom's prediction of spiral collapse was wrong. The idea of gradual energy loss assumes the electron is a ball moving along a path. A ball can slow down continuously. A standing wave cannot decay continuously. It has no mechanism for gradual change. It either holds its pattern or it breaks to a new one. And because this is all confirmed physics, verified by experiments and calculations that agree with each other, to an extraordinary level of precision, the next step was to actually see these wave patterns directly. Scientists eventually built instruments capable of imaging individual atoms and mapping the electron probability clouds around them. What they found was either deeply satisfying or slightly unsettling, depending on your relationship with equations that turn out to be perfectly stubbornly right. In 1981, two physicists at IBM's research laboratory in Zurich, named Gerd Binnig and Heinrich Rohrer, built a microscope unlike anything that had existed before. A conventional microscope uses light. Light has a wavelength, and you can't resolve details smaller than the wavelength of the light you're using. At the atomic scale, visible light is useless. Atoms are thousands of times smaller than the wavelength of visible light. Binnig and Rohrer's instrument used electrons instead. Their scanning tunneling microscope worked by bringing an extremely sharp metal tip, ideally just one atom wide at its point, to within a few atoms width of a surface. At that distance, electrons from the tip could tunnel across the gap to the surface. The current produced by that tunneling was exquisitely sensitive to the exact distance between the tip and the surface, and to the electron density on the surface beneath the tip. As the tip scanned across the surface, the instrument mapped the electron density at every point. The result was a three-dimensional map of where electrons were concentrated across the surface. In other words, a direct image of electron probability, clouds. The images that came back from these instruments matched the quantum mechanical orbital shapes exactly: the spherical smears of s orbitals, the double lobes of p orbitals, the dark nodes between the lobes, the regions of zero probability, visible as actual dark bands in the images. Every feature that Schrödinger's equation predicted in the 1920s showed up in photographs taken 60 years later. Binnig and Rohrer won the Nobel Prize in Physics in 1986 for this work. The confirmation carried a weight that years of indirect experimental agreement couldn't fully provide. You could look at the image. You could see the probability cloud. The math had predicted a specific shape, and the shape was there. Not approximately, exactly. And the precision of that match isn't just visual. Quantum mechanics as a whole, including the orbital picture built from Schrödinger's equation, has been tested against experiments to 15 decimal places of accuracy. To understand what 15 decimal places means, consider this comparison. If you calculated the distance from New York to Los Angeles and your answer was accurate to 15 decimal places, your error would be smaller than the width of a single hydrogen atom. That's the level of agreement between quantum mechanical predictions and measured reality. No other theory in the history of science comes close to that precision. Quantum mechanics is the most accurately tested framework humans have ever constructed. Every test run against it, across a century of increasingly precise experiments, has confirmed it. The electron clouds are real, the orbital shapes are real, the probability distributions are real. And once you accept that, a question follows immediately. What happens when two of these probability clouds get close to each other? When the electron wave function of one atom starts to overlap with the electron wave function of another? The answer is the foundation of all chemistry, and it's stranger and more beautiful than the simple picture of atoms sticking together ever suggested. Every scientific theory lives or dies by experiment. You build a model, you make a prediction, you run the measurement. If the prediction matches, the theory survives. If it doesn't, you go back and rebuild. Most theories in science match experiments to 2 or 3 decimal places. A good theory might hit 5. Exceptional theories push to 8 or 9. These are already extraordinary achievements, the result of decades of careful work by thousands of scientists with increasingly precise equipment. Quantum mechanics matches experiments to 15 decimal places. This number needs a physical comparison to feel real. Imagine stretching a measuring tape from one side of the continental United States to the other, roughly 3,000 miles. Now imagine your measurement of that distance is accurate enough that your error is smaller than the diameter of a single human hair. That's roughly the ratio of precision quantum mechanics achieves in its predictions versus the scales involved. The specific measurement physicists use to demonstrate this is called the anomalous magnetic moment of the electron. An electron has a magnetic property related to its spin. Quantum mechanics predicts the exact strength of this magnetic property using a long and complicated calculation. Experiments measure it directly using extremely precise instruments. The prediction and the measurement agree to 15 decimal places. 15. Every digit. Matched. No other scientific theory humans have ever produced comes close to this level of agreement with experiment. Quantum mechanics sits alone at the top of that list. This matters for everything discussed in this video. The orbital shapes, the probability clouds, the wave functions, the energy levels, the spin states, the uncertainty principle. All of it is part of the same quantum mechanical framework, the framework that predicts electron behavior to 15 decimal places, the same math that generates the image of the s-orbital sphere and the p-orbital dumbbell is the math that has been verified against experiment more precisely than any other body of knowledge in human history. The picture of electrons as probability clouds isn't a rough model that might be replaced by something more precise later. The underlying framework is already so precise that any future theory whatever eventually extends or replaces quantum mechanics will need to reproduce these predictions to 15 decimal places as a minimum requirement. The electron cloud picture is as solid as scientific knowledge gets, and this precision has a practical consequence that extends far beyond physics labs. Every semiconductor in every computer chip, every laser in every optical fiber carrying internet data, every medical imaging machine using nuclear magnetic resonance, every solar cell converting light to electricity. All of these technologies were designed using quantum mechanical predictions. They work because quantum mechanics is right. The global economy runs on a foundation of 15 decimal place accuracy. And the most immediate application of all this precision, the one that makes chemistry possible, the one that makes your body possible, happens when 2 electron clouds meet. What occurs at that meeting is something the classical picture of atoms never adequately explained, and something that quantum mechanics describes with startling clarity. 2 hydrogen atoms drifting toward each other. Each one is a single proton with a single electron. The electron of each atom exists as a spherical probability cloud, an s orbital, centered on its proton. As the 2 atoms get closer, those clouds begin to overlap. In the region between the 2 nuclei, the 2 electron wave functions meet, and wave functions, like all waves, can either reinforce each other or cancel each other, depending on their relationship. When the 2 wave functions add together constructively, the probability density between the nuclei increases. The combined cloud becomes denser in the space between the 2 protons. Both electrons now spend more of their time in that shared region. And here's the physics. Both protons are positively charged. When electron density builds up between the 2 protons, those electrons are simultaneously attracted to both protons. They pull the 2 protons toward each other. At the same time, The electron cloud being between the protons partially screens each proton from the other's repulsion. The result is a stable configuration. The two atoms don't fly apart, and they don't collapse into each other. They settle at a specific distance apart where all the forces balance. The two electrons, now shared between both nuclei, hold the system together. This is a covalent chemical bond, the most common and important type of bond in chemistry. And it only works because electrons are waves. A classical particle electron couldn't be shared between two nuclei simultaneously. A particle is either here or there. A ball can't be in two places at once. Two atoms sharing a classical particle electron would mean the electron ping-ponging back and forth, which would produce an average attractive effect, but not a true stable bond. An electron wave function can be spread across both nuclei at the same time. The probability cloud can extend continuously over both atoms. The electrons genuinely occupy the space between and around both protons simultaneously. This shared wave function is called a bonding molecular orbital. It's a new wave function that spans both atoms, lower in energy than the separate atomic orbitals. Lower energy means more stable. The system prefers this state. The atoms stay bonded. Every molecule in existence is held together by this process. Water, carbon dioxide, every amino acid, every protein, every strand of DNA in every living cell, every material scientists have ever synthesized, all of it built from overlapping wave functions. Electrons shared between atoms through the mathematics of quantum mechanics. Remove the quantum wave nature of the electron and chemistry stops working. You have protons and electrons, but no way to hold them into stable molecules, no complex structures, no biology, no life. But the wave nature does something even more surprising than simple bonding. Electrons can pass through energy barriers they classically should be completely blocked by. This quantum tunneling isn't just an exotic edge case in a physics lab. A team of researchers proposed in 2023 that it's the physical engine running underneath every single chemical bond in existence. The covalent bond sounds simple when described as atoms sharing electrons, but what sharing actually means at the quantum level is worth slowing down on, because the stakes are everything. When two atoms bond covalently, their electron wave functions don't just touch at the edges, they merge. They combine into a new single wave function that belongs to neither atom alone, but to the bonded pair together. The electrons described by this combined wave function are delocalized, spread across both atomic nuclei simultaneously, in a cloud that spans the entire molecule. This merged wave function is lower in energy than either of the separate atomic wave functions. Lower energy is more stable. The bonded state is the state the system naturally falls into when two atoms get close enough. The electrons, in finding the lowest energy available to them, effectively hold the molecule together as a consequence. Pull the wave functions apart, and the bond breaks. The electrons return to separate atomic orbitals. Each atom reclaims its own electron cloud, and the molecule ceases to exist. The bond is the shared wave function. Full stop. Now scale this up. Water is two hydrogen atoms and one oxygen atom held together by covalent bonds. The specific shape of water's bonded molecular orbital, the way the wave functions combine, gives the water molecule a bent geometry with oxygen slightly negative and each hydrogen slightly positive. That geometry makes water a polar molecule. That polarity makes water dissolve salts. That dissolving ability makes water the universal solvent for life on Earth. Everything water does, everything that makes it essential for biology, traces back to the shape of its molecular orbital wave function. Proteins are chains of amino acids, each amino acid connected to the next by a covalent bond between a carbon and a nitrogen atom. The wave functions of those bonds determine the bond's angle, its strength, and how the protein chain folds. The folded shape of the protein does. What proteins do determines whether you're alive. Every enzyme that drives chemistry in your cells, every receptor that responds to a signal, every structural protein holding your cells in shape, All of it is wave function geometry playing out trillions of times per second inside every cell of your body. And the bonding situation goes even deeper. Researchers publishing in 2023 proposed that electron tunneling, electrons passing through energy barriers they classically cannot cross, is the fundamental physical mechanism behind all chemical bonding. Every bond type, covalent, ionic, polar covalent, hydrogen bonding, all of them mediated at the deepest level by the quantum wave nature of electrons, allowing them to cross barriers classical particles could not. This is still a theoretical proposal under active research, classified as a scientific theory rather than confirmed fact. But if it holds up under further testing, it means the quantum weirdness of electrons doesn't just enable bonding at the edges, it is bonding at every level for every molecule that has ever existed. The universe is made of matter. Matter is made of atoms. Atoms bond through electron wave functions. Every structure in existence is a consequence of quantum mechanics operating continuously, invisibly, at the smallest scale of physical reality. And here's what nobody has fully explained yet. What happens to the wave function the moment you measure it? Picture a ball rolling toward a hill. If the ball has enough energy, it rolls up and over. If it doesn't, it stops, rolls back, and never makes it to the other side. Classical physics is rigid about this. The ball either has the energy or it doesn't. There's no middle ground. Now replace the ball with an electron. The electron approaches an energy barrier, a region of space where it classically lacks the energy to exist. According to classical physics, it should stop and turn back. According to quantum mechanics, there's a real probability the electron appears on the other side anyway. This is tunneling, confirmed by experiment, measured with precision, built into technologies billions of people use every day. The reason tunneling happens comes directly from the wave nature of the electron. A wave doesn't stop at a barrier the way a ball does. It diminishes as it enters the barrier, but if the barrier is thin enough, some of the wave emerges on the other side. Where there's wave function on the other side, there's probability. Where there's probability, there's a real chance of finding the electron there. The thinner the barrier and the lighter the particle, the higher the tunneling probability. Electrons are light enough and quantum enough that tunneling is a routine part of their behavior. Scanning tunneling microscopes, the instruments that imaged electron orbitals directly, work entirely because of this effect. The microscope tip gets close to a surface, but never touches it. Electrons tunnel across the gap between tip and surface. The current produced by that tunneling is what the microscope measures. Without tunneling, there's no current, no signal, no image. Flash memory, the storage technology in every phone and solid-state drive, uses tunneling to write and erase data. Electrons tunnel through a thin insulating layer to become trapped in a storage cell, or tunnel back out when erased. Every file on your phone is stored and retrieved through controlled quantum tunneling. The nuclear fusion that powers the sun depends on tunneling. Two protons need to get close enough to fuse together, but they carry the same positive charge and repel each other fiercely. Classically, the temperature in the sun's core isn't high enough to force them together. They shouldn't be able to fuse. But protons are quantum particles too, and they tunnel through the repulsive barrier with a small but real probability. The sun fuses enough protons per second to release its energy because quantum tunneling tips the balance. And now the proposal from 2023 connects this to chemistry at the most fundamental level. Researchers argue that when two atoms bond, what's actually happening is that electrons tunnel continuously through the energy barriers between atomic potentials, not just occasionally, but as the constant ongoing mechanism of the bond itself. The shared wave function of a covalent bond, described in the last chapter, may be better understood as continuous tunneling across the barrier between the two nuclei. This would reframe every chemical bond ever described, every bond in every molecule, every reaction in every living cell, all of it running on electron tunneling as its engine. Confirmed theory, or still under test? The precise framing is a theory supported by strong mathematical arguments, published in a peer-reviewed journal, but awaiting broader experimental confirmation. Either way, tunneling is real, pervasive, and central to the physical world. And the deeper you look into quantum mechanics, the more it raises a question that sits at the boundary between physics and philosophy. The electron's wave function spreads through space, a three-dimensional cloud of probability describing all the places the electron might be found, some regions dense with probability, others thin, the whole structure shifting and oscillating according to Schrödinger's equation. Then you measure it. You run an experiment to detect the electron's position. You get an answer. The electron is here, at this specific point in space. The wave function, which was spread across the entire atom a moment before, is now collapsed to a single location. This is wave function collapse, and it's one of the most discussed and least understood events in all of physics. What actually happens during the collapse? Schrödinger's equation evolves the wave function smoothly and continuously. It doesn't predict collapse. The equation says the wave function should keep spreading, keep evolving, keep existing as a probability cloud. There's nothing in the equation that says it suddenly snaps to a point. Yet every experiment shows that it does. Every single time you detect an electron, you get one definite position. Every time, the spread-out wave function produces a single definite result upon measurement. The probabilistic cloud becomes a specific fact. And the moment after measurement, if you measure again immediately, you get the same answer. The wave function has collapsed, and the electron is localized. How this happens physically remains one of the genuinely open questions in physics. The process is confirmed. Wave functions collapse upon measurement. This is not in dispute. It's been reproduced millions of times across an enormous variety of experiments. The fact of collapse is rock solid. What causes it? What physical mechanism drives the transition from spread-out wave to single point is unresolved and sits classified as an open mystery. Some physicists argue that the measuring device, by interacting with the electron, forces it to settle. The interaction between the quantum system and the classical measuring apparatus causes the wave function to select one outcome. This is the practical answer most working physicists use to get through their calculations. Some argue that the wave function never actually collapses. Instead, every possible measurement outcome becomes real, in a branching structure of parallel realities. This is the many worlds interpretation, and it handles the math cleanly without needing a collapse mechanism, because no collapse ever happens. Every outcome occurs somewhere. Some argue the collapse is related to consciousness, that an observer must be aware of the result for it to become real. This view is held by very few physicists today and is considered highly speculative. None of these interpretations change the experimental predictions. All of them reproduce the same results. The experiments cannot distinguish between them. The question of which one describes reality is, at the moment, unanswerable by any known method. Wave function collapse is real, its mechanism is unknown. This is what physics looks like at its frontier. Extraordinary precision in prediction, sitting alongside complete ignorance of mechanism. And the interpretations physicists have built around this problem are among the strangest ideas in the history of scientific thought. In the late 1920s, Niels Bohr and Werner Heisenberg developed what became the dominant interpretation of quantum mechanics. They called it the Copenhagen interpretation, named for the city where much of the discussion happened. The central claim is deliberately minimal. The wave function is a mathematical tool for calculating the probabilities of measurement outcomes. It is not a description of physical reality between measurements. The electron doesn't have a position between measurements. The question of where the electron is when nobody is measuring it is, according to Copenhagen, a question without meaning. Physics only speaks about what you can measure. Everything else is outside its domain. This sounds reasonable until you push it. If the wave function is just a calculation tool, and the electron has no real state between measurements, then what is actually out there? Copenhagen's answer is effectively, we don't ask that question. The theory predicts outcomes. Asking what reality looks like between measurements introduces concepts the theory doesn't need and can't address. Bohr defended this position vigorously and famously clashed with Einstein over it for decades. Einstein believed that the wave function had to be incomplete, that a more complete description of reality must exist. Underneath, one where particles have definite positions even when unobserved. He spent years designing thought experiments trying to show quantum mechanics had gaps. Every time the experiments designed to test Einstein's intuition sided with quantum mechanics. In 1957, a physicist named Hugh Everett proposed a completely different answer. What if the wave function never collapses? What if Schrödinger's equation just keeps running, evolving the wave function continuously, and every possible measurement outcome actually happens? When you measure an electron and get a specific position, that's because you, the measuring device, and the electron are now entangled. The wave function has branched. In one branch, the electron is here and you see it here. In another branch, the electron is there and you see it there. Both branches are equally real. Both versions of you exist, each seeing a different result, each unaware of the other. This is the many worlds interpretation. It requires no collapse mechanism because nothing collapses. The wave function always obeys Schrödinger's equation. The apparent collapse is just your branch of reality becoming definite from your local perspective. The many worlds picture is mathematically clean. It has no hidden mechanism to explain. It takes quantum mechanics at face value and runs it to its logical conclusion. It also implies that every quantum event that has ever happened has produced branching realities. Every radioactive decay, every photon absorbed by a molecule, every electron measured in a lab, an unimaginable tree of branching universes, growing continuously. Then there is de Broglie's own answer, developed later by physicist David Bohm. The electron is a real particle with a real position at all times, guided by a real physical wave called the pilot wave. The particle always has a definite location. The wave function describes the actual physical wave guiding it. Collapse is what happens when the wave's structure changes due to interaction. All three interpretations make identical experimental predictions. There is currently no experiment that can choose between them. Which one is true is among the deepest open questions in science. Here is the situation. Quantum mechanics makes predictions. Those predictions are tested against experiments to 15 decimal places. The theory is right. That part is settled. But the question of what the theory means, what it says about the physical reality underlying the predictions, has three serious competing answers. Each one describes a completely different universe. Copenhagen says, physical reality between measurements is a concept that doesn't apply. The wave function is a probability calculator. The electron has no properties until measured. Many worlds says, physical reality is the wave function and it never collapses. Every outcome of every measurement happens in some branch of a constantly splitting structure of parallel realities. Pilot wave says, the electron is always a real particle with a real location, guided by a real wave that fills space. The apparent randomness comes from our ignorance of the electron's precise starting position, not from fundamental indeterminacy. Three completely different pictures of reality, three completely different answers to the question of what the universe is made of at the deepest level. And every experiment ever run produces results consistent with all three simultaneously. This is the measurement problem, and it's one of the most remarkable situations in the history of science. A theory of extraordinary predictive power, the most precisely verified framework humans have ever built, sits on top of a foundation where the basic question of what is actually happening has no agreed answer. Physicists work with quantum mechanics every day and produce results that drive technology, medicine, and material science, all without needing to settle which interpretation is correct. The math works regardless of which picture you prefer. The predictions come out the same. Some physicists view this as a sign that the interpretational question is meaningless, that asking what the wave function really is falls outside the scope of physics, similar to asking what exists outside the observable universe. Others view it as the most important unsolved problem in all of science, a sign that our understanding of reality at the deepest level remains fundamentally incomplete. There have been proposals for experiments that might distinguish between interpretations. Most require technologies that don't exist yet. Some researchers argue that certain interpretations predict slightly different results under extreme conditions that are presently impossible to test. The debate continues, active, unresolved, fascinating. And while physicists argue about the nature of reality, there's a more immediately uncomfortable fact. Sitting in every classroom around the world, the model most students leave school carrying in their heads is the one that everyone agreed was wrong over a century ago. The clean diagram with the electrons on rings, the planetary atom. And what students miss by stopping there is more than a technical update. It's a completely different picture of what matter is. Every year, millions of students learn about the atom using a model that physicists abandoned in the 1920s. The Bohr model. Electrons on rings. Clean, neat, wrong. Why does it keep getting taught? The honest answer is that it's useful for specific purposes. Bohr's model correctly predicts the emission spectrum of hydrogen. It gives students a visual framework for understanding that electrons occupy different energy levels and that atoms absorb and release light when electrons jump between levels. For introductory chemistry, those ideas are enough to explain a lot of reactions and behaviors. The model is also simple. You can draw it in 30 seconds, a nucleus in the middle, a few circles, some dots on the circles. Every student can picture it. Every teacher can explain it without requiring 3 semesters of mathematics first. The wave function picture requires calculus, complex numbers, and 3-dimensional probability thinking before the shapes even become visible. Most high school curricula don't have room for that, so the Bohr model stays as a teaching shortcut with the intention that students who go further will eventually learn the real picture. The problem is that most students don't go further. Most people who learn the Bohr model in school never revisit it. The rings stay in memory as the real picture of the atom. The electron becomes permanently in their minds, a tiny ball on a track. And with that image comes a set of assumptions about what matter is that are fundamentally incorrect. If the electron is a ball on a track, matter feels mechanical, solid, predictable. You can imagine atoms as small billiard balls, bouncing off each other, stacking neatly, building up into materials in a way that feels graspable. If the electron is a probability cloud, a standing wave, a spread-out quantum structure that exists in multiple states simultaneously until measured, then matter becomes something stranger. The solid table is solid because of quantum exclusion, not because its atoms are packed tightly like marbles. The molecules in your body are held together by shared wave functions, overlapping clouds of probability locked into stable geometries by quantum rules. The two pictures produce different intuitions about what the physical world is. The Bohr picture makes matter feel like a collection of small objects following rules. The quantum picture makes matter feel like a set of mathematical structures that happen to produce stable, persistent patterns in space and time. Neither picture fully prepares you for the deepest implication of all, the one that turns the everyday experience of solidity, weight, texture, and permanence into something that rests on a foundation of quantum rules operating silently beneath everything. Everything around you is made of atoms. Those atoms are held in shape by quantum mechanics. The electrons in those atoms are not sitting still. They are not orbiting. They are probability clouds, standing waves, spread out quantum structures locked into specific configurations by rules about energy and exclusion and uncertainty. The solid world you experience is an emergent property of quantum fuzziness, organized by mathematics into stable, persistent patterns. And that changes what matter even means. Look at your hand, the bones underneath, the cells packed together, the molecules building those cells. the atoms making those molecules. Every atom in your hand is mostly empty space. The nucleus occupies a volume roughly 100,000 times smaller than the atom itself. If you scaled a hydrogen atom up to the size of a football stadium, the nucleus would be the size of a marble sitting at the center of the field. Everything else is electron cloud. The solidity of your hand is not caused by atoms pressing against each other, like solid balls. Your hand feels solid because the electron clouds of your atoms resist being forced into the same quantum states as other atoms nearby. Pauli's exclusion principle, operating simultaneously across every atom at every surface, produces a repulsive pressure that stops matter from passing through matter. Touch a wall, and the reason you can't push through it isn't that the wall's atoms are packed too tightly. It's that the electron wave functions of your hand's atoms and the wall's atoms cannot overlap without violating Pauli's rule. The rule generates a force. The force pushes back. The sensation of solidity is quantum mechanics made physical. The weight of an object comes partly from the electrons resisting compression. The texture of a surface is a map of electron cloud distributions. The color of a material is the result of which photon energies its electrons can absorb and which they release. Everything sensory about the physical world traces directly to the quantum behavior of electrons. And it goes further. The chemistry that makes your body work runs on electron wave function overlap. Every enzyme, every DNA strand, every membrane, every signal passing between neurons, all of it is molecular machinery built from atoms bonded through shared electron wave functions. You think because electron clouds in your neurons organize into molecular structures that process signals. You exist because electron clouds in your DNA hold the code for building you, replicate it with quantum-level precision, and execute it continuously in every cell. The universe allowed life because quantum mechanics allowed stable, complex molecules. Quantum mechanics allowed stable, complex molecules because electrons obey wave equations that produce specific orbital shapes. Specific orbital shapes allowed the right atoms to bond in the right ways. The right bonds built chemistry. Chemistry built biology. Biology built you. All of it resting on the behavior of particles so small they don't have definite positions, held together by rules about probability and exclusion and uncertainty, described by equations written 100 years ago by a handful of physicists who argued intensely about what those equations meant. The electron is a wave, a cloud of probability, a standing pattern of quantum possibility that collapses to a point the moment you force it to declare a location, then spreads out again the instant you stop looking. And somehow, out of billions upon billions of those spread out, fuzzy, uncertain quantum structures, interacting and excluding and overlapping and tunneling, the world you see and touch and live in emerges, specific, persistent, real. Your hand is made of uncertainty, organized by mathematics into something you can feel. That is what matter is.